Today we'll be discussing about the second module contents with respective to the subject called as VLSI design. Basically in the second module we will have a discussion on fabrication. So how exactly the fabrication is done, and the focus is only with respective to CMOS fabrication. And after we go ahead with the understanding of the CMOS fabrication, we are supposed to understand the layout. So in order to generate the layout, what are the prerequisites? So that also has to be discussed. So the prerequisites to study or to understand the layout is to understand the stick diagram, and to understand the stick diagram you are supposed to understand the schematic representation. So we will be having a discussion with different logic gates and as well as different combinations of logic circuits. After that we go into the topic called as VLSI design flow. So whenever we are supposed to go ahead with the fabrication, what are the design flow involved, and introduction to CMOS technologies, introduction and what exactly are the different CMOS technologies, layout, design rules. And these are contents which are belonging to text 2. Next we have parallelly another topic which is MOSFET scaling and small geometry effects. So all the while we are going to shrink the size. So as we are shrinking the size, we are supposed to do the scaling, and parallelly once we do the scaling, are there any drastic effects which are affecting the environment or the working condition of the IC? That is called as small geometry effects, and along with that we are going to discuss about MOSFET capacitances. This is with respective to text 1. So text 1 is CMOS digital integrated circuits designed by Sung Mo Kang and Yusuf Leblibisi, and text 2 is CMOS VLSI designed by Neil West and David Harris. So we go ahead with this topic called as CMOS fabrication and layout. So how do we go ahead with this? Transistors are fabricated on thin silicon wafers called as a substrate. So already we are having a brief knowledge about how the cross-sectional view of a transistor looks like. So we need to consider it from the beginning, which is the substrate, which is nothing but a thin silicon wafer. So substrate can be either N-type or P-type depending on what type of transistor we are going to construct. So we can examine the physical layout of transistors from two perspectives. One is the top view, which is just observing from the top, and the other one is cross section. So cross section is observed by slicing the wafer, cutting it in the middle vertically. So this helps us to give the cross sectional view. And we then along with this, during fabrication we are required to have a set of masks. So what are the different masks used in fabricating a IC, and specifically we are talking about a logic gate called as an inverter. And what should be the size of the transistors and the wires, which is as per pertaining to the mask dimensions. So this is the cross-sectional view of an inverter. You notice, so this is your substrate. On your substrate you have an well structure. So here it is an N-well structure. On an N-well structure you have two types of P diffusions, and this is your N substrate. This is your this is your N P substrate, and you have P type of diffusions. And likewise you have the polysilicon structure over here, which is nothing but our gate terminals. So since this is a condition of a inverter, the source of PMOS is grounded and the drain of PMOS and drain of NMOS are connected, and this is where we take the output, and this again is connected to the ground. The PMOS is connected to the supply VDD. So this is a cross-sectional view. So what is it you observe? The cross-section of an inverter is seen built on a P-type substrate. So normally the condition taken here is inverter is seen being constructed on a P-type substrate. P-type substrate means it is positive charge carriers. So P-type substrate means it is helping us to construct a NMOS transistor. So the PMOS transistor requires an N type of a body. Therefore, if you have P substrate, you can create NMOS transistor. But how will you create PMOS transistor? So in order to create a PMOS transistor, you need to have N substrate, but already available substrate is P type. So how do you create an N substrate? So N substrate is created by a well structure here. That is what has been discussed here. So the PMOS transistor requires an N type of body region. So an N well is diffused into the substrate. So this is how an N well structure is created, and with respect to dimensions. Normally this is 6 micrometer deep. So identify the regions to create the well structure and do the necessary dopings. So on P substrate you are doing N diffusion, and that in turn is nothing but your N type of well. Similarly, so if you have N substrate, you can construct PMOS transistors. PMOS transistor is the one which is constructed on N substrate. So this is your P substrate, PMOS transistor. And since I have already told you that this is a P substrate, it is possible for us to construct two types of N terminals here, N diffusions, and therefore N type of transistor. This becomes your NMOS, this becomes your PMOS. And do the necessary connections, that becomes your inverter. So the NMOS transistor has heavily doped N type source, and yeah, as I told you, this is P substrate, so this is N type, this is N type. One is your source, one is your drain, and in intermediate is your gate. And this is how. So polysilicon is constructed, already we know this, polysilicon is constructed on a thin layer of silicon dioxide, SiO2. So thin layer of SiO2, which is nothing but gate oxide, also called as gate oxide, is the first and the foremost step required in fabrication. So as we have already had a discussion, PMOS has P-type source and drain regions. Okay, we are just talking about the two types of diffusions, which is very much clear. Now gates of the two transistors form the input A, because in CMOS transistor, in CMOS inverter, two inputs are shorted, and that is your input. Two inputs are shorted together in order to form the common input, single input A, and in inverter there is only one output, therefore the two drains are also shorted. The source of the NMOS transistor is connected to the ground line, and the source of the PMOS transistor is connected to the VDD line, as I have already told you. Or if you want to understand much better, we can show you the representation of a CMOS transistor, which is like this. What I have been telling you, the two gates are shorted and they form the input. So this is your input and this is your VDD, and the two junctions, the drain junctions. So one terminal is drain and the terminal is also drain. This is what is your output. And what is the output in an inverter? This is nothing but whatever is the input, the complement of that is your input. The complement of that is your output. So this is your VDD. Now which are the terminals which should go to VDD? Which are the terminals which should go to VSS? Since the output is taken at the drain junction, obviously the other terminal left out is the source, and this is the source. And in CMOS, the pull-up region, this is the pull-up region. So the pull-up region is always PMOS. Pull-up region is always PMOS, and in the bottom region, this is always P-type, and in the bottom region, it is your pull-down, which is your NMOS. Pull-down. This is your ground and this is your supply. Therefore, what is there on the top region is your PMOS, and the two inputs are shorted. So, PMOS source is connected to VDD. That is what I am telling. PMOS transistor source of PMOS is connected to VDD, and source of NMOS is connected to ground line. And the intersection of the two drain terminals, the drains of the two transistors are connected to form the output Y. Okay, instead of calling this as V0, let me call this as Y. And the thick oxide of silicon dioxide, called as the field oxide, prevents metal from shorting to other layers. Okay, so what is the purpose of oxide here? It sees to it that the bottom layer or the bottom substrate with the diffusions and the well structure are safe. They are not damaged. So oxide helps us to manage the bottom layers to be safe. The substrate must be tied to a low potential to avoid forward biasing the p-n junction. Please understand here, in the substrate, what is it you observe? What is the type of the substrate? P-type. What is the type of the well structure? N-type. What is the type of diffusion you have? If this is P substrate, the diffusion is N-type. So there is a possibility for so many p-n junctions to be formed in the substrate. P-n, 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 P-n. So there is a possibility for so many junctions to be formed, and there is also a possibility that at one instant of time they can become forward biased and they start conducting. So the junctions, when they are existing, it will always be forward biased and it starts conducting and a leakage current flows. So the leakage current in turn abruptly varies the threshold voltage. So variation of threshold voltage will have a drastic effect on so many parameters, and number one, the drain current is going to change. Therefore, see to it that the junctions here are not going to conduct. Therefore, how is it possible? The only possibility is to connect the substrate to ground. So the substrate must be tied to a low potential to avoid forward biasing the p-n junction between the p-type substrate and n-type source or drain. As I told you, p-n, p-n. So this is how. Likewise, the n-well must be tied to a high potential. So this is connected to high potential, which is nothing but your VDD. So that is also possible for avoiding the junctions being formed in the well structure. So this is how we are able to see to it that no current conduction occurs in this particular substrates. Next we begin with the fabrication process. So the fabrication sequence consists of a series of steps and are defined through the process called as photolithography. So photo is something with the help of light. Lithography is something which you are going to write and scrape and all such things. So smaller transistors are faster because electrons don't have to travel. Therefore, preference is given to generate small transistors. And the inverter could be defined with the help of 6 masks. So what is mask? It avoids the bottom layers to be either diffused or affected by other layers. So what are the different masks? N-well mask, polysilicon mask, N plus diffusion mask, P-type diffusion mask, contacts and metals. So these are the different types of masks which are being used in the fabrication process. Alright, we will have a look at this. Now we have different types of maskings. Now you just check what is this. This is your polysilicon. This is your polysilicon and this is your diffusion. This is your diffusion. Therefore, transistors are being formed here. PMOS transistor and NMOS transistor. Therefore, this is a well structure being created here. This is your ground and this is your supply. So this is the fabrication model which has the transistor version from top. If you see, this is how it looks. So this is your NMOS transistor. And first type of mask, how basically we start with the substrate. After the substrate, the first and the foremost step is to create a well structure. What type of well are we creating in the speed substrate? The type of the well we are creating is the N-well structure. So create a mask which is called as N-well mask. I hope I am clear. So this is the structure which is called as N-well mask. So when you see this kind of a structure, apart from this area, rest all N-well is created. So this is your N-well mask. Next we have polysilicon mask. So only in this area you can see polysilicon being deposited, or N-well can avoid, this can be avoided. Masking can be done here and only here N-well can be created. It depends how particularly this technology is being used. Next type of masking is N-diffusion mask. So since you are constructing it on a P substrate, as we have seen from the earlier diagram, this whole thing requires N-diffusion. Next is P diffusion. Next is contacts. Wherever you require contacts, this is where you require contacts. So contacts are here. Rest all no contacts. And finally your metal which is helping us to pull out the leads. So this is where your polysilicon is coming out and different materials, different terminals like source, drain and gate with the help of VDD and VSS. So this is how the different maskings are represented. So the process begins with the creation of an N-well on a bare p-type silicon wafer, as I have already told you. So figure A illustrates the bare substrate before processing. And how is it possible to create N-well? So N-well is formed by adding group 5 dopants. So in group 5 you have phosphorus, which is a pentavalent element, and as a result when you are putting it into a silicon substrate, the silicon substrate changes from p-type to n-type. To define what regions receive N-wells, grow a protective layer of oxide over the entire wafer, then remove it where the wells are required. So what is the process required? First and foremost, before creating the well is to grow a layer of oxide. So oxide acts as an insulator and the bottom layer is protected. Then where do you want the well? That particular region you have to scrape the oxide. And that particular region you are going to do the N type of diffusion. So this starts the N type of dopants. So understand, identify the region where you want to create the N well structure. The other area where you don't want the N well structure is already safeguarded by the oxide. So even though you make the N diffusion to fall on the oxide layer, the bottom layer is safe and it is not going to get contaminated. Next, how is it possible for us to create a well structure? So, the well structure is possible by heating the wafer. Wafer is first oxidized at high temperature. So, it is heated at a very high temperature in the range of 900 to 1200 degrees Celsius, and oxygen air is made to fall on that. Therefore, what exactly is your substrate? Silicon. Silicon, when it is oxidized, when it is coming in contact with oxygen, it reacts and therefore it forms an oxide. So that is why we are often telling this as growing a layer of oxide. It is not building or it is not applying. It is in turn growing a layer of oxide. Then the oxide must be patterned to define the N well. As I told, you have to identify which is the region where you want the well structure. So that helps you to identify the well structure. Before that, an organic photoresist that softens when exposed to light is spun on the wafer. I will just go ahead with the diagrams later on. So after oxide, you are applying a layer of photoresist. So what exactly is photoresist? It is a layer which is not at all reacting with photo. In other words, light. When light is made to fall on the substrate, it has no reaction. The bottom layers are not affected. So photoresist means it will not have any impact of light on the bottom layers. And one more beauty of this photoresist is whenever you expose it to light, it is softened. So the region of the photoresist which is not exposed to light is hard. The region which is exposed to light is soft. So I want to create a well structure. Then in that case, the region where I want to create the well structure, only there I want to expose it to light, and the other regions I don't want it to expose it to light. So the region which is exposed to light is soft, so it can be scraped. That is what is told in the next step. The softened photoresist is removed to expose the oxide. Now we will have a look at the diagrams B, C and D. Okay, well, maybe probably in the next slide. So let me go along with the explanation first. Then the oxide is etched. Alright, it is scraped out. Oxide also. First, what is it? We are trying to create a well structure. So oxide is etched with hydrofluoric acid where it is not protected by the photoresist because the layer has become that region which is not avoided from light. That means it is exposed to light, it is soft and it is removed. Then the well is formed where the substrate is not covered with oxide. I hope I am clear. This is how the well is created. After the well is created, you need to create the diffusion into that well. A depth is created. Well is nothing but a deep layer is excavated. And there you need to create the necessary dopants, or you need to do diffusion with either positive charge carriers or negative charge carriers, thus forming N well or P well. So how is that done? Two way to add dopants are by diffusion and ion implantation. So the procedure of making the well as N-type or P-type is taken care by two procedures called as diffusion and ion implantation. So what exactly is diffusion? What exactly is ion implantation? In the diffusion process, the wafer is placed in the furnace. Alright, the wafer is placed in the furnace with a gas containing the dopants. So what is the dopants we want? N-type. So you fill that with N type of gas, saline. Saline is the gas, and you place that particular masking you have to do, N-well masking, and you have to place it in the furnace where it is filled with saline gas, which is going to do N diffusion. When heated, the dopant atoms diffuse into the substrate. They just go and enter into the substrate which is not masked. This is the procedure involved in diffusion. But what is the procedure in ion implantation? Dopant ions are accelerated to an electric field. That is, what is a dopant? What is the type of dopant I want? It is the pentavalent element or the phosphorus. And the ions, phosphorus ions are accelerated, are made to move with the help of an electric field and blasted into the substrate. So finally, N type of elements are made to move and sent into the substrate. In either method, the oxide layer prevents the dopant atoms. I told you, oxide layer, apart from that you also have a masking. So in either case, it is possible for us to do the diffusion. So expenditure is also there. I hope diffusion is comparatively little less expenditure it consumes rather than ion implantation. So this is the procedure involved in doing the diffusion or in doing the necessary dopings. So the two procedures are diffusion and ion implantation. So this is what I was talking. Initially you have the substrate, expose it to oxygen, oxidized. So heat it at a very high temperature and expose oxygen into oxygen chamber, and that is how you have silicon dioxide. And next grow a layer of another layer called as photoresist. Then this photoresist, when it is exposed to light, this becomes hard, and this region is not exposed to light. Therefore, it can be removed, it can be etched. So already you must have got a view that this is the place where an well structure is being created. And next, scrape the oxide also. You notice the oxide is also removed. Now what is it you observe? Photoresist is also removed, only oxide is there, and you have almost a well structure being ready, and do the necessary process of either diffusion or ion implantation in order to make it of N type. Finally, you notice this is your well structure. Okay, this is how the well structure is being created. Next, after creating the well structure, the next step is to form the polysilicon. So, transistor gates are formed consisting of polycrystalline silicon. So, what exactly is the procedure? How to create a polysilicon? Okay, I was wrong, sorry. Polysilicon is created with the help of silane gas. Sorry, I told in diffusion, wrong it is. So the wafer is created in a reactor with saline gas and heated for polysilicon layer deposition by chemical vapor deposition. So what exactly is this procedure? Take a gas, silane gas, it is HSiH4. Heat it to a very high temperature. When you heat it to a very high temperature, the gas is converted, that whatever that gas is there, it is almost creating vapors. That vapor is made to deposit, and that is how your polysilicon layer is created. So once the polysilicon layer on either side, both two types, you want it on well structure as well as on the substrate. So parallelly polysilicon is created. So what is the other name for your polysilicon? It is nothing but your gate. Then you have to introduce the N regions. So first you have to see to it that you are creating N region for the substrate area, not the one which is in your well. Your well requires P regions. Therefore, for well, well region should not get affected. Therefore, a protective layer of oxide is formed, and that is called as N diffusion mask. We will notice that in the diagrams later on. So the entire N region, N well region is masked. So either side, on the left side is the place where you are going to create your N diffusion, in other words which is nothing but your P substrate. Then the N regions are done into the identified regions by a procedure called as ion implantation. Either you can use diffusion or ion implantation, and this is called as N diffusion. So almost on your P substrate you are having N type, therefore you are constructing an NMOS transistor. And polysilicon is taken care. Therefore there is a process which is called as self-aligning. What do you mean by? Notice that the polysilicon gate over the MOS transistor blocks the diffusion. And this process is called as self-aligning because the source and the drain are automatically formed. So once you have the polysilicon and you do the necessary diffusion, obviously it is possible to have a N-type region, especially the source and the drain. So by itself, since polysilicon is already created, by itself the other two terminals are created, and this is called as self-aligning. Similarly, this process is repeated for P diffusion mask. What is P diffusion? The one which is inside the well structure. And oxide is grown finally. The metal used is aluminium. So metal aluminium is used wherever the contacts are required. It will fill into that particular place and evenly coating is done, and that is how the metal contacts are also finally established. In case there is any extra metal over the surface, it will be scrapped. It will be etched. So this completes the simple fabrication process. You can look into this diagram. So N well is created, polysilicon is made to deposit on the every region. Where it is required, only there we will take care of polysilicon, and where it is not required it will be removed. So you can notice this is your polysilicon, this is your polysilicon, and below that you have an oxide. The oxide here is called as thick oxide. Next you are going to form the diffusion on the P substrate. So on the P substrate you are trying to form the diffusion, and since it is P substrate, what is the type of diffusion you have to do? N type. This is called as self-aligning. So when you have the gate, this is understood that this is the place for your source and drain, and only in this region the N diffusion occurs through a procedure called as ion implantation. Once the source and the drain of the P substrate is created, focus is done inside the well structure. So inside the well structure you need to, polysilicon is already created, so create place for your P diffusions. Likewise P diffusions are created in this particular space 1, 2.